Okay, so now we're jumping into 10.2 of the chapter, and we're looking at planar graphs and Eulers' formula. So Euler was actually the guy who developed network and graph studies. It all came about in sort of the 18th century from a town in Germany. Really interesting actually if you want to look it up, but let's get into some of the mathematics behind it. So we're looking at connected graphs, and this is how we start getting into planar graphs. So this is just some of the background that you're going to need to know. So connected graph means that every vertex is actually connected to the graph, so it's accessible. So you can actually use an edge to get to it. So you can see here that this top, move this out of the way, this top graph here is connected because you can actually get from every vertice, or get to every vertice and from every vertice. This one down here isn't connected because, as you can see, B is an isolated vertex. It's out on its own, means it's not connected. So for a planar graph, there's simply two requirements. So it must be a connected graph, so one of those graphs that we've just seen, the top one where every point is connected, and it can't have any edges that cross over. So you know how when we were looking at the number of faces in a graph and we might have had to redraw it so that there were no intersections in any of those edges? Again, same thing, none of the edges can cross over. So on the left here, I've got a non-planar graph that has been drawn. So as you can see, all the point vertices are connected, use correct terminology, but the line AD and CE actually cross over and intersect. There's no vertex in the middle there, they just simply intersect. So this is a non-planar graph, so we do have to redraw it. So all we've done is we've taken the information and just basically changed it up. So you can see that. It should contain the same information, but it actually doesn't. So there's actually a line missing on this graph. So as you can see, we can get from A to B. Yep. A to F, but we're actually missing the edge A to D, so that needs to be drawn in. So we've got to draw in that line A to D. So then we've got C to D and C round to E. We've also got the E to D and the E to C, and F to E, B to C, so on and so forth. So again, make sure, like I needed to, that you have got the same information transferring over and creating your planar graph. So that is now a planar graph because there are no edges crossing over and all of the point vertices are connected. So what is Euler's formula? So he came up with a formula to determine whether or not a graph is planar. So it looks at the relationship between the vertices, edges and faces in a graph. So it's given by this formula here. So vertices plus faces minus edges is equal to 2. And then down the bottom here, they're just been transposed or rearranged depending on what value you're trying to find or what values you've already got. So if you're looking for the number of vertices, the number of faces, or the number of edges, or if you've been given the vertices and faces and you want to try to work out, you know, what E plus 2 is. But yeah, this is the formula that we're going to be working with. So let's work through some of these questions now and have a look at actually applying this formula. Okay, so I had to go and find my question that I wanted to use. So here it is. I've just pulled an example out of the textbook, but I find often that although it might be in the textbook, breaking down what it's actually talking about in the instructions is sometimes quite difficult. So it's given us this original graph here, and it's asking us to redraw it so that none of the edges intersect. Again, that is one of I guess the requirements of being a planar graph. So what I'm going to do is I'm going to stop doing that to me, computer. Take my vertices and draw them up. So I'm going to make that P. Need to turn this function off. So I've got P, T, and I'm going to label them as I go. Q, R, and S. So now I know that I've got a connection. Get my computer to catch up to what I want it to do. So in my original graph, I've got a connection from P to T, and P also connects to Q, and then P also connects to R. Okay, so I've done my P vertex. Okay, so moving on to T. Now T again goes back to P, T then goes to R, and T also goes to S. So that's my degree 3 T. So R is only degree 2, it goes to P and to T, so I've got R done. Now to S, it goes to T, but it also goes to Q. Now I can't run the edge inwards or straight across because it's going to run into these edges here or this vertex R. So what I'm going to do is I'm going to make it an arch over the top, just like that. It's as simple as that. Edges can be curved, they can wiggle, they can go round different vertices as long as they're not intersecting, so that you can make it a planar graph. So that's that redrawing there. So the next part is that it wants us to use Eulers' formula. I guess, and let's work in proof that Eulers' formula works. So remember that it was given to us, so vertices plus faces minus edges is equal to 2. So how many vertices have we got? So we've got P, T, S, R, and Q. So 1, 2, 3, 4, 5. So we've got 5 vertices. Faces, how many faces have we got? So we've got this one in here. Remember that the faces must be enclosed within at least 3 edges. So we've got 1 here, 1 in this space, and then outside as well. So that's 3 faces. And then we're going to take away the number of edges. So we've got 1, 2, 3, 4, 5, 6 edges equals 6. Now, what does this give us? 5 plus 3 is equal to 8 minus 6. Look at that, equals 2. So if this works and gives us the correct answer, it actually means that the graph can be drawn as a planar graph. Right? So that's working with Eulers' formula.